Hey there, and welcome back to the Deep Dive. Today, we're tackling a really fascinating challenge in AI. How do we make these huge pre-trained models like transformers even more nimble, more
Mhm.
adaptable, especially when they hit brand new tasks, often specialized ones, without having to retrain them completely from scratch?
Mm,
These models are incredibly powerful, sure, but that real-world agility, well, that's still kind of the frontier.
exactly. We tend to think of AI training as this massive one-shot deal, right?
Mm.
But what if there's a fundamentally different way, almost like a surgical approach,
Yeah.
a way to significantly boost performance after the main training, like right at the moment they face a new problem? That's really where the cutting edge is pushing now, trying to get more out of these models.
And that's exactly where our deep dive is headed today. We're diving into this really innovative concept called test time training, TTT for short. It sounds pretty amazing, the idea that these sophisticated models can actually refine themselves, on the fly, and with really minimal data to dramatically improve how they learn and perform. Honestly, it almost sounds too good to be true, but the research we've looked at suggests, well, it suggests it's real.
Yeah, we're going to unpack the core mechanics behind TTT. We'll look at the key parameters, the things that really dictate how effective it is, and we'll uncover some, frankly, surprising theoretical insights into why this adaptive approach works so well. Because this isn't just about small tweaks. We're talking about a provable improvement in in-context learning. It's a real leap.
Okay, so our mission today: unpack how test time training fundamentally enhances the way transformers learn in context. We want to give you a shortcut to understanding this powerful new frontier in AI. We've pulled together some fascinating stuff from recent academic notes, some groundbreaking papers to guide us. Let's jump in. So, right out of the gate, the big question: what exactly is test time training? How is it fundamentally different from, the traditional training or fine tuning we usually talk about?
But what's really fascinating here is that TDT isn't about retraining a huge model. It's not even fine-tuning in the traditional sense with a big labeled dataset. Instead, it's more of a strategic maneuver. You take an already pre-trained model, like a transformer, and you perform a very quick optimization step, just a tiny adjustment, using a small, often unlabeled dataset that only becomes available right at test time when the model is actually being used.
Okay, hold on. Unlabeled data at test time.
Exactly. Think of it like a brief surgical calibration.
Mm.
Right when the model faces a new situation, it allows it to adapt precisely to that specific task. It's a big conceptual shift, moving away from thinking of deployed models as totally static.
That is a crucial distinction. So it's not a full re-education, more like a quick on-the-spot adjustment. Can you walk us through how that adjustment actually works, like under the hood?
Precisely. And the core innovation is how efficient it is. Often, it involves just a single gradient descent step. Now, for listeners, imagine the model's trying to find the best solution, like finding the lowest point in a hilly landscape. A gradient descent step is just taking one small step downhill towards that best point. TTT does this just once,
Just one step.
just one. It takes the model's existing knowledge, let's call it its weight matrix W, and it just nudges it slightly to a new state, WTT. The math looks like WTT, WHL
Okay, break that down a bit.
Sure, W is the starting knowledge. Eta is just the size of the step, how big a nudge. And LHARD STTW is the direction downhill, based on the error the model makes on that small batch of new test time data. So you adjust the old knowledge by a small amount in the direction that immediately reduces error on the new stuff. And this single step, amazingly, results in what's called a rank 1 update for linear attention models.
Rank 1 update. Okay, that sounds mathematically important. What does that actually imply for the model, how it learns?
That's a great question. Without getting lost in the linear algebra weeds, a rank 1 update is a very efficient, very focused kind of change. It means the model isn't like totally rethinking everything. It's making a highly targeted, direct modification, focusing on aspects relevant to the current task. Think of it like adding one precise brushstroke to a painting, not starting over.
Ah, okay, so it's fast adaptation without the huge computational costs.
Exactly. That's a major innovation here.
That makes perfect sense. A swift, targeted calibration, not a full overhaul. Now, any complex system like this has its dials, its levers. What are the key parameters that really influence how well this test time training actually performs?
Right. That's the critical next question. What determines the outcome? The research points to three crucial parameters that directly impact performance, especially the model's loss. First, there's N. That's the number of fixed context tokens or samples you give the model in the prompt.
So the examples you provide up front.
Yep. They're like the clues you give the model to understand the new task, like giving a few relevant sentences before asking a question.
Okay, so N is the upfront context. What else?
Second, we have D. That's the dimension of the input features. Basically, it reflects how complex or rich the data is. Think high D for detailed images, maybe lower D for simpler numbers. And third, there's K. That's the number of query samples in that test time training set we talked about.
The small batch of new data for the adjustment.
Exactly. That small batch of new, maybe unlabeled data used for that single gradient step. It's the immediate feedback driving the adaptation.
So N, D, and K, context, complexity, and test time data size. Are there specific combinations or relationships between these that are particularly insightful?
Yes, absolutely. And this is where the theory starts to give us real predictive power. The research highlights two really important ratios derived from these parameters. These ratios help us understand how the model behaves at scale. First one is alpha and ED.
Okay, N over D, context samples divided by feature dimension.
Right. It tells us how much context information is available relative to the data's complexity. Are we giving lots of examples for simple data or just a few examples for really complex stuff?
Makes sense. And the second ratio?
That would be gamma, okay, GABD. So the number of test time training samples divided by the feature dimension. This shows how much data we're using for that quick refinement step, again, relative to the complexity. These ratios, alpha and gamma, are fundamental. They're key to the theoretical predictions and understanding the scaling laws of TTT. They help predict behavior across different models and data.
Okay, so we have this elegant single-step update. We understand the key parameters N, D, K, T, and the ratios alpha, gamma. But the big question, the bottom line, does test time training actually improve performance? And can we measure that improvement? This is where it gets really exciting, right? Moving beyond just intuition.
Absolutely. And this is one of the central, really profound findings, a significant academic breakthrough, I'd say. Test time training provably improves transformers as in-context learners. And we can quantify this improvement. We measure it by looking at the model's loss. Remember, lower loss means better performance. So TTT gives us a quantifiable boost. We can actually predict how much better it gets.
Provably. That's a strong word. What does having that level of mathematical certainty really unlock?
It's huge for researchers, for practitioners. For example, in simpler cases, the improvement in loss, the difference between the starting loss and the lower loss after TTT, can be approximated by a surprisingly precise formula. It looks something like K plus D, D2N plus DET.
Whoa, okay. That looks dense.
It does, but let's break down the concept. The KK plus D part, it basically says the more test time samples you have relative to the complexity D, the bigger the improvement. Makes sense. The DN plus D part. It suggests that if you started with less context, N, for a given complexity D, TTT has more room to make a difference. And that last term, PTT, relates to the inherent difficulty or magnitude of the new task itself. The amazing thing is this approximation becomes exact in large-scale scenarios. It gives us a scientific way to predict the benefit, not just guess.
Wow, that is precise. Moving from hunch to formula. Incredible. But the paper also mentions some intriguing or non-monotonic behaviors. What does that mean for the loss? And how does alpha, that context to complexity ratio, play into these, let's say, surprising trends?
Yeah, this is where it gets even more nuanced and interesting. The research clearly shows this fascinating non-monotonic trend. As you change alpha, which is N overall, the loss doesn't just steadily go down or up.
So adding more context doesn't always mean TTT helps more?
Not necessarily in a linear way. The amount of improvement TTT provides can actually diminish as alpha increases beyond a certain point. Think of it like tuning a radio. You turn the dial, it gets clear, but turn it too far and it might get fuzzy again before clearing up later.
Yeah.
There are complex interplay points. For large models and complex data, the improvement is roughly proportional to 1 alpha plus 1.
1 over alpha plus 1 cubed, so it drops off pretty fast as context alpha increases.
It suggests diminishing returns on extra context, specifically for the impact of TTT. However, for a fixed amount of context, alpha, the improvement is proportional to GO plus 1. Remember, gamma is KID. This tells us that adding more test time training samples, K, pretty much always helps, proportionally. Which is good news, practically speaking.
Okay, so context is tricky, but more test time data, K, is generally good. That's useful. Now, what about the starting point? Does it matter if we start with a really well-trained model, RW, versus, well, nothing, a blank slate, a null model, before applying that single TTT step?
That's a crucial comparison, and it leads to a really fascinating discovery, actually. The research looked into this. Start with the optimal pre-trained W, or start from basically zeros, a null matrix, 0 to XD, and then do the TTT step. And what they found is a threshold. Depends on K, the number of test time
That's
samples.
threshold.
For
Okay.
smaller values, yeah, starting with the pre-trained W is better. That makes intuitive sense, right? You have a head start.
But I sense a but coming.
There is. As N gets larger, increases beyond a certain point. Surprisingly, the null model, starting from nothing, can actually perform comparably well, or sometimes even better, after that single TTT step.
Wait, really? Starting from scratch can beat a pre-trained model just with enough test data and one TTT step?
In some scenarios, yes. It suggests that enough new, relevant data combined with the power of that gradient step can sometimes overcome a complete lack of pre-training. It really highlights how potent PTT itself can be. It's not just a fine-tuner, it can almost act as a powerful initializer under the right conditions.
That's wild. A single step compensating for potentially years of pre-training.
Okay.
Now, this has mostly been under specific, maybe simplified conditions. What happens when we get to more general real-world situation?
Yeah.
Where data structures are messy, features are correlated. Reality, does TTT still hold up?
It absolutely does. And this is where the theory gets really powerful. The analysis extends to what are called general covariance matrices. For listeners, think of it this way. In real data, features aren't usually independent. Stock prices might move together, weather patterns are linked. Covariance matrices capture these complex relationships. So when the theory handles these, it means the insights apply to much richer, more realistic data. In these general cases, the paper defines two important quantities. Let's call them A and B.
Okay, A and B, what do they represent conceptually?
Think of A as measuring the misalignment. How different is the new task from what the model already learned during pre-training? How surprising is it? And B represents the sort of magnitude or strength of the model's existing knowledge. Now, Theorem 5.3 is key here. It shows the loss improvement for TTT is approximately K plus D, A plus B.
Okay, so that A squared on top looks important.
Exactly. This is a profound innovation point. It mathematically shows that when this misalignment measure A is larger, test time training actually achieves greater performance gains.
Ah. So TTT works best when the model actually needs to adapt more, when there's a bigger gap between its training and the new task.
Precisely. It's most impactful when the new task's characteristics are significantly different from the pre-trained model's assumptions. Or, technically, when the task's covariance aligns well with the direction the model needs to change. Imagine a model trained on news articles, now asked to analyze social media posts. There's relatedness, but also significant differences misalignment. TTT would likely provide a big boost there. It gives us a theoretical reason for where TTT will provide the biggest bang for the buck.
That's incredibly useful for knowing when to apply it. Okay, so we have these elegant proofs, these intriguing insights, even for complex data, but the proof is in the pudding, right? Does this theory actually hold up with real transformer models out in the wild?
Yeah, that's the crucial validation. And the answer is yes. The experiments really back up the theory quite well. For instance, they showed TTT's effectiveness on a model called TAB-PFN.
TAB-PFN. Sounds like it's for tabular data, spreadsheets and the like.
Exactly. It's a specialized transformer for that kind of data business, finance, science data sets, things with rows and columns. And the experiment showed TTT significantly boosted its accuracy, just as the theory predicted, depending on the amount of context in it. Seeing it work well there is a big deal because it shows TTT isn't just for language or images.
Right, broad applicability. What about more famous models?
Well, they also tested it on GPT-2, a model many people know. And again, the results were compelling. They looked at the loss after TTT, and it clearly showed that starting with the pre-trained weights generally led to lower loss than starting from the null zero initialization, especially as K, the test time data size, increased. So it reinforces that TTT provides a robust, consistent boost, and crucially, the real-world results closely match the theoretical predictions. That alignment is key.
It really bridges the gap between theory and practice, then.
Fantastic.
Yeah.
Wow, what a deep dive. We've really gotten into the weeds of test time training. We saw how this surprisingly simple single-step process can provably boost transformer performance. We explored those critical parameters, N, D, K, and the ratios alpha and gamma that govern how well it works. And we even understood those surprising non-monotonic behaviors of loss and when starting from scratch might even be viable.
And we uncovered that really neat concept of misalignment, how it beautifully explains when TTT delivers the biggest gains. It lets us leverage these powerful models much more efficiently on new, diverse tasks. And the fact that the theory lines up so well with real-world tests That really marks a significant step forward in understanding adaptive AI.
So what's a big takeaway here for you, our listener? We're really looking at a potential future where AI models aren't just powerful, but also incredibly adaptable, able to learn and refine themselves on the fly without needing these massive, costly retraining cycles that could fundamentally change how we deploy and manage AI systems long term. Yeah, and it raises some really important questions for what's next. It's a fascinating frontier. The research itself points to exciting future work, like expanding TTT to different, maybe more complex architectures, softmax attention, multi-layer models, exploring different ways to validate it, maybe even using unsupervised or semi-supervised approaches for that in-context learning boost. So the big question becomes, how much further can we actually push this idea of in-context learning, especially by combining these deep theoretical insights with even more complex, messy, real-world scenarios? Could we unlock a whole new level of AI agility?
A really powerful thought to chew on as we wrap up. Thank you so much for joining us on the deep dive today. We hope this conversation sparks your own curiosity to explore more.